Assalamu alaikum, brothers. Welcome to this session. This is the first episode in this session for digital hardware design. If you've been following my channel, you would know that I have a YouTube channel and I conduct courses, cohorts, online and on-site. If you go to my playlist, so I've already made the almost all the videos required for level 1. I'll be adding some more in level 1 as well. I've just started uploading videos in level 2, and I'm conducting live courses both online and on-site for level 1. Now, I actually wanted to go step by step, but right now, for instance, these are the levels. So if you go to my website, and here is the presentation about this program that I'm running. It's called Circuit Builders program. And I've already completed almost all the videos that are required for the Foundation of Electronics course. I've started putting the videos up for the Analog Electronics course. But I'm skipping these two levels right now, and I'm jumping on to, in fact, all these three levels, and jumping on to digital hardware design. The reason is that because I need to do a project in FPGA, and I wanted to upgrade my knowledge, upgrade my skills. So I thought, why not take people along on this journey rather than doing it myself? So I've started. This is the first video. It's a test video. I'll see whether I can continue doing it or not. So a bit of introduction. This is my area of work. Digital hardware design is my area of work. I've worked in this area and I've taught this area for many years. And the last project that I did, this is the case study for that. And it was an HMAC core, not really a core, but it was almost a core that I wanted to, that was needed to be deployed on a site for authentication. And I made that in Verilog. This was back in 2023. At that time, the AI was just coming in the market, and it was at least not adopted by our company at that time. And what I did was that I took this Shaw code that was available in OpenCores, and I built another architecture around it. Like, this was a complete architecture. And then I designed the data path and the controller part of the design, and then I designed the flowchart, the ASM for it. Then I wrote the code for it, simulated it, and then deployed it. Right. So this was the project that I did around a few years back. So now that I want to come back and do another project, there are things that have changed. The things that have changed is that the AI is now being extensively used by developers, even in the area that I'm working in, first of all. And secondly, my main development language, hardware, HDL that I used was Verilog. And I wanted to migrate to system Verilog. So I thought, why not start making videos for this. So the quality of these videos will not be very high in terms of, I will not be spending a lot of time editing these videos, because I'm a one-man show, right? And there's only so much I can do. So I don't want to waste a lot of time in editing the video. So I'll just put it out there just the way it is. And secondly, all the previous courses that I'm uploading on YouTube, they've been in Urdu. This course, I was just thinking maybe I should do it in English, just because I want to reach a wider audience. And those people who actually reach this level of digital hardware design are generally familiar with English. So I thought, why not try to reach a wider audience by making these videos in English. So this is an introduction. So I'll keep things very, very brief. I will assume that those people who are attending this course, they are already familiar with basics of electronics, basics of analog electronics, like transistors, op-amps, and resistors and the like, and they're aware of basic digital systems. If you've attended a course called Digital Logic Design, if you're aware of AND gates, OR gates, and multiplexers and all that stuff, and a bit of simulation, then you are good to go, right? If you've attended a course in microcontrollers or microprocessors, that's even better. I will probably be creating videos for these, but not right now, because right now I'm going to be focusing on FPGAs and RTL, and I will assume that you are aware of these basic knowledge that is required to jump into FPGAs, right? So let's start. So let me quickly, in this first session, I will quickly introduce what FPGAs are, and it'll be very, very brief. It will not be very, very technical. It'll be, let's say, very non-technical in terms of, I'll not go into the depth of what's actually happening. I'll just give enough information for you to absorb what FPGAs really are if you're aware of basic electronics and basic digital systems. Transistor, as we know, can also be used as a switch. Oh my god, this is so ugly. Anyway, so let's say this is the transistor with a resistor at the base, and I'm using it in either cutoff mode or in saturation mode. That means I can use it as a switch. Now a basic, now how can I make a gate from this? Let's say if I just put a resistor over here and take a V out from here, and I have 5 volts over here and I have ground over here, right? So when I give a high, let's say 5 volts over here, then this will be shorted to ground and my output will be 0. So this in essence is a NOT gate. A NOT gate is represented like this, and I'm sure you are aware of the truth table for a NOT gate. For instance, if the input is A and the output is F, so A and F, so if input is 0, output will be 1. If input is 1, output will be 0. So this is the basic of a NOT gate. So if, and then similarly we can make an AND gate using transistors. So I'll just make one more gate, and you can explore how other gates can be made. So this is, for instance, this is not the actual construction of an AND gate. This is kind of like just for us to understand how transistors can be used to make gates. So this is a resistor. I've tried to draw a resistor over here. I hope you can understand what I'm drawing right now. So this is the same 5 volts. So if this is A and this is B, let's say for instance, if both are on, then the voltage over here will be high, that means 5 volts, and you will get an output of 1. So drawing the truth table, when you can iterate through all possible inputs of A and B. For instance, this is the truth table. I hope that if you have done digital systems, you know what a truth table is, and this is out. I'll call it F. So for all combinations, you can try this out, that you will actually get the output as like something like this, right? So it will only be high when both are 1. So the point I want to make is that you can use transistors to make gates. So the main 3 types of gates are a NOT gate, AND gate, and OR gate. So this is the NOT gate, which inverts the input. So if A is like this, then F output will be equal to A bar. That means it is be the inverse of A. And we have an AND gate, and if you have A and B, then the output F will be equal to, it can be written something like A dot B, or something like that. So if both A and B's are 1, you'll get output 1, otherwise it will be 0. And the third is the OR gate, which is a bit tricky to draw when I'm trying to draw on the screen. Okay, and A and B. So when either of these is 1, you will get a 1, otherwise it will be 0, and it is represented by A plus B like this. So this is not important, right? What I want you to take you to is what is actually an FPGA. So starting from a transistor, you know what gates are, and gates can be used to make more complex designs. Like for instance, you can implement truth tables, any kind of truth table for instance, if you have a truth table for a full adder, like if you have A, oh come on, where's the pen? If you have an A and B and you want to add them, the sum, and you have a carry, right? This is really ugly. I don't know if you can really understand what I'm trying to do over here. Next time I'll try something else. This is 0 0 0 1 1 0 1 1. So if for this, the sum of this will be 0, sum of this will be 1, and the carry will be 0 for both of these. Sum will be 1, carry equal to 0. When both are 1, sum is 0 and carry is 1. For this, I am assuming that you know a bit of binary logic as well. So these are all assumptions that I'm taking while I'm going to be going through this course. Okay. So if you know this, then you know that any function can be implemented using a truth table. And lastly, if you know that, then you know that you would know what a multiplexer is. So if you have a multiplexer, for instance, 2-pin, you have a one select line, so you can select either of these lines by this select line, right? A, B, and select line. And if you have studied digital logic, you know that almost any truth table can be implemented using a multiplexer. This is where FPGAs come in, because the core of FPGAs is that it has an infrastructure of so many truth tables, you can say. And all the truth tables, for instance, if you have a truth table of, let's say, which is capable of taking, let's say, 6 inputs, A, B, C, D, E, F, and G, and you have an output. You can implement this if you have a big enough multiplexer. So assume that a logic cell or a logic element inside an FPGA has a big multiplexer that can implement any truth table. Okay, so this is the building block of an FPGA. You can call it a logic element. Okay, or it has a big multiplexer, or you can call it a lookup table. It's called a multiplexer, or in terms of FPGAs, it's called a LUT, lookup table. Lookup table is the same as a truth table, so it can be used to implement any function. And then you have a memory unit, which is a flip-flop. If you have studied digital logic, you would know what a flip-flop is. So basically, a logic element is a LUT plus a flip-flop. This is the simplest form of a logic element. More advanced logic elements have some other features as well, but we're not going to go into that. So if you are using an FPGA, what FPGA is actually whole thousands and thousands of lookup tables. So you have, we can say, logic elements. So you have thousands and thousands of logic elements. They are stacked in kind of like a matrix, like this, and you have a lot of lines, like programmable pathways that you can use to connect one logic element to another, thereby allowing you to create more complex logic. So in essence, it is actually a blank real estate, in fact, which has elements that can be used to implement almost any logic. So there is no fixed architecture other than availability of these resources that can be used to create almost any function. And there are thousands and thousands of them. So what we do is we don't program each one of these logic elements by hand. We use a language which is called an HDL, hardware description language, or so there's a language that can be used to describe hardware. So for instance, if you want to create an AND gate, for instance, so you would say output function A equals to A, and then a symbol of AND and then B. So if you need to know what hardware will be created when you write a code like this, right? So you need to write hardware aware code. So each line of code translates into some piece of hardware. It will create some piece of hardware which will eventually be mapped onto one of the lookup tables, right? So you must know what the tool. Now what you will do is we'll write a piece of code which will describe hardware, and then we'll give this piece of code to a tool called a synthesis tool. A synthesis tool then is a tool that understands the architecture of the FPGA, and it also understands the HDL, and it saves us the pain of physically programming all of these lookup tables. So what we do is we give our code to the synthesis tool, and we tell it and we give it the constraints that we want it to use for the synthesis process. And what it does is that it translates it into some kind of a hardware architecture like this, and then it maps it onto these resources that are available on the FPGA. And this is the fastest way to prototype high-speed designs, like for instance, designs that are used to implement algorithms and stuff like that. So I don't know if I was able to convey the basics of FPGA, but I wanted to keep it very, very brief. So if there's some aspect that you don't understand, maybe tell me in the comment section, and I will try to explain it. And let me know if this kind of video is actually helpful for you, because it does take some time and effort to make them. And I would only want to continue making them if actually it benefits somebody. If it doesn't, then why waste time? Anyway, so thank you very much for joining me. If you have been here throughout this session till now, then I'm really grateful. It will help me if you give a comment, or maybe just give me a thumbs up. It's not for the sake of monetizing the channel. It gives me the encouragement to carry on. So thank you very much. Until next time, take care. Assalamu alaikum warahmatullah.